Alright, so I know somebody's gonna bitch about this, right? So it's talking about Cauchy sequences here, right? Now, let's look at this. Okay, so what this is, Cauchy, pretty sure, yeah, I don't care, it's French. Anyway, so what's happening here is what we're doing is if it just keeps getting closer and closer together as we go forever, then it's a Cauchy sequence. And if it doesn't, then it's not. Okay. Okay. So if it actually ever hits the limit, it's not a Cauchy sequence. That's why the integers are not continuous with no gaps under this definition. Because it'll just terminate. Okay. The rationals don't terminate. When you do this, when you're using rationals as input, where the fuck am I supposed to? There it is. When we're using rationals as the inputs to a Cauchy sequence, right? They don't terminate, right? You can keep going smaller and smaller and smaller and smaller because they're dense. Okay. So denseness is related to continuousness. Okay. But what we'll say is that the rationals, if we're using rationals, they can output irrationals. So they're not within the... Right, so you can get a convergent sequence of rationals that gives you an irrational. Okay. I don't have a problem with that. My problem is I don't see how this actually entails continuousness. Or how the rational numbers, giving us the irrational numbers, definitely closes all of the gaps. Or how that even gives us all of the irrationals. Like, there's a shit ton of assumptions here. There's a shit ton of assumptions here that this even works. And the way that it's phrased here, it doesn't, like, yeah, the reason that you have to put in parentheses Cauchy sequence is because the thing that you said doesn't actually uniquely identify a Cauchy sequence. Okay? Like, that's the reason that you have to put it in parentheses, because you said it wrong. So you have to clarify. So why not just clarify in the first place? Why not just say it right in the first place? Right? Because if I do what it says, ignoring the parenthetical, I can get this to work with integers. I can also get it to work with rationals. Under the same... Actually, it's going to work more similar to a Cauchy sequence with rationals and staying within rationals, right? So what we can do is we can just keep steering close. We can just keep steering to other rationals, right? There's no... Right? It says every sequence that keeps getting closer together will converge to a limit in the set. If what we're doing in the rationals actually follows what we just said here, it's gonna do that because it's dense. Even though we're gonna be skipping, like we're gonna skip over stuff, it's always going to yield something in the set. It's always going to converge to a limit in the set. You can always define it that way. So what you're doing is you're choosing to ignore that possibility in order to say that it says what you want it to say. So why should I accept that after all of the other mistakes in here? Why should I accept that this makes sense when it doesn't? This definition, as it's given to me, works for integers and natural numbers. It works everywhere. It works everywhere. These all, by this logic, they're all continuous. Right? The natural numbers is an infinitely large set. Okay? Right? It's infinitely large. Okay? So any sequence within that, within the natural numbers, okay, what we're doing is we're converging within there. We only have, it's closed under addition, it's closed under multiplication. So those are the only things that we can use, right? We can't use subtraction or division, right? We're not allowed to use those operations with the natural numbers, okay? So every sequence that keeps getting closer together, how do we even get that to work, first of all? Right? The only way is to be able to just generate random lists that are where like the endpoints are closer together than they were in the previous version of the list. That's the only way we can do this. And under that definition, we are now going to converge on a limit that is in the set. So that behaves as this is stated. And the natural numbers are not continuous. So this definition fails. We can do the same thing for integers. We can do the same thing for rationals. We can do the same thing for anything. Any infinite set you can do this for.